All right. We're putting the M and E and M with magnetic fields produced by electric currents. This is section 4, okay? I'm going to introduce to you a magnetic field equation, okay? This is the formula for magnetic field strength created by this is very important, okay? Magnetic field strength created by a straight current carrying wire, okay? And that is going to be B equals mu naught, okay, times I over 2 pi r, okay? And what does everything mean in the context of this? What does everything mean in this equation, right? B is the magnetic field created by wire, okay? R is the distance from that wire. Okay, that's where B is being measured. Okay, and then I is the current in the wire. Okay, I mean, you could probably guess that, right? Okay, is the current in the wire, okay? And one thing to note, too, is that mu naught is a brand new variable, right? We haven't seen it before. This is called the permeability of vacuum. Okay, and you're going to see this in the Physics C formula sheet, okay? So let me show it to you. You're going to see this in the Physics C formula sheet. Maybe make sure my light's off so it doesn't catch a glare, okay? You're going to see that we have vacuum permeability and vacuum permittivity, and those are two different things, okay? So you need to make sure you're looking at permeability when we're talking about magnetic field strength, okay? And you'll see that's mu naught is equal to 4 pi over 4 pi times 10 to the negative 7th, okay? So what's going to happen is, wait a minute, the value of that is 4 pi times 10 to the 7th Teslas times meters over amps, okay? Wait a minute. If we substitute mu naught, okay, if we make that substitution in here, okay, then you'll notice that what happens is we get B equals 4 pi times 10 to the 7th, okay, times the current, I, which we don't know. I mean, this is, again, we're just making substitutions with constants, okay? 2 pi r. Wait a minute, we've got we can actually knock out 2 pi in this equation because it's in common on both in both terms, right? So that's what I'm going to do. I'm going to knock out 2 pi, okay? And the 4 pi will then change to just 2. So then you can actually get a simplified form of the equation, which is just 2 times 10 to the 7th times I, okay, over r. And this is just a shortcut, okay? This is a shortcut for the equation. I mean, it cancels out to that. And you might be thinking, well, why is mu naught why is mu naught equal to that when we can cancel it out there? This is the only time that you can really cancel it out, okay? We use mu naught in other things, okay? So we just, we can simplify it in that one case. Don't think that this is something that works every single time. It obviously depends on the case, okay? Okay, around each of these straight wires, okay, you're going to use your right-hand rule, okay, to get the magnetic field around them. And what we should see, right, this is going into the page, okay? So I'm going to just stand up and do this, right? Okay, thumb goes into the page, and my fingers are curling clockwise, right? So you'll notice that we get this, okay? And this actually stretches out even further, okay? It's not just limited to this small area. It actually stretches out pretty far. Okay, this one's coming out of the page now, so my fingers are curling counterclockwise, okay? I drew this terribly, oh my gosh. Wow, okay. Terrible, okay? And then this is going to the right, okay? So that's what I'm going to do. I'm going to go to the right, okay? Into the page below the wire, and then above the page, out of the wire, okay? Into the page below, out of the page up top, okay? What about right here? Again, right-hand rule, thumb goes in the direction of the current, okay? or so thumb goes in the direction of the current. We go into the page on the right side of the wire and out of the page on the left side, okay? So we get into the page there, out of the page on the left side of the wire, okay? All right. Pretty straightforward, okay? Now, we've got two wires in each of these cases, okay? One of them's coming into the, we got both going into the page and then one going in and out of the page, okay? So what are we going to do about that, okay? I'm gonna color code the wires first off, okay? We'll do I'll make this the green wire right here, okay? And this is the blue wire, okay? Okay, now first off, right, this is going into the page, so I need to figure out the direction of the magnetic field as a result of this wire, okay? So thumb into the page, curls in clockwise, okay? So we're gonna go clockwise. Okay. The blue wire, same thing, goes into the page, it's also gonna be clockwise, okay? Now, I'm gonna warn you against just assuming that into the page always means clockwise and out of the page always means counterclockwise, just because I hate making like these really like broad blanket statements about things, okay? For the green field, notice that what's actually happening is we can take the circle, we can expand it, we can stretch it out to cover infinity, right? If we stretch it all the way out, what's the direction going to be at point P? It should be down and to the right, right? Then, for here, if we stretch this out, it should go up and to the right, okay? And so you should end up getting a net field that goes directly to the right. We're going to call this B net, okay? It's not where you launch Overwatch from, okay? It's the net magnetic field, okay? What about this other example right here? We've got one going into the page, one coming out of the page. Well, we already know into the page, okay? We just did it earlier, okay? Oh gosh, I sent that pen flying at me. We already did it earlier, right? The end of the page one is going to go clockwise, okay? Okay. And the out of the page one is going to go counterclockwise, right? So it goes, out of the page, right? We're going counterclockwise, okay? So then, okay? You might be thinking, oh, but don't they cancel out? Well, they probably cancel out dead center between them, but this is not dead center between them, okay? So point P is from the purple is actually going to go down and to the right, okay? And then from the orange, it's going to go down and to the left, okay? Notice the horizontal components cancel out, okay? And you're left with a brand new B net that's going straight down, okay? Okay. Our next example shows us two long wires, right, that are perpendicular to each other, and they carry currents of 100 amps and 200 amps in the directions shown, okay? Point P is 0.01 meters from the 200 amp current and 0.02 meters from the 100 amp current as shown in the diagram. What's the net magnetic field direction and magnitude at point P? Well, first things first, the easiest thing to do is going to be to figure out the direction of the magnetic field from each wire. So we have the 200 amps going up and to the right, okay? I'm gonna zoom out so you can actually see my hand, okay? Mr. Mitchell hand reveal here, okay? Up and to the right, and it's going into the page below, or I guess to the right or below the wire, and then out of the page above the wire or to the left of it, okay? So we'll go out of the page above, so we have dots up here, okay? And then below it, we're going into the page. So we've got X's down here. Okay. What about the 100 amp current? Well, again, I'm gonna have to really reorient myself here, okay? Current's going down this way. We're going below the wire, we're going into the page, and then on the other side, we're coming out of the page, okay? So we should have X's below the wire, okay, and then dots above it, okay? So, oh gosh, that means that the magnetic field at point P, they're opposing each other, okay? But at least they're both parallel to each other, which means that we don't really have to do any trig yet, which is great. I don't want to have to do trig, okay? Let's solve for the actually, let's do the orange wire first, okay? This is well, that's not orange. Let's do our orange wire first, okay? Here's our orange wire, okay? And then here's our green wire up here. Okay. Okay, let's solve for the orange wire first. The magnetic field, I'm going to call this B1 because it's 100, okay, is equal to mu naught times the current in 1 over 2 pi the distance from 1, okay? And if we plug in everything we've got here, well, first off, let's simplify, right? We can actually knock out the 2 pi, right? We talked about simplifying this earlier. Okay, so you should end up getting something that's like 2 times 10 to the negative 7, okay, times 100, and the distance is 0.02, okay, you end up getting 0.001 Tesla, or that can be safely turned into 1 millitesla, okay, and that's going out of page, okay. B field number 2, again, mu naught times the current in 2 over 2 pi R2, okay? Then what you would do is you can use the simple form, right? That's going to be the easiest way to do this, okay? 2 times 10 to the 7th, okay? Is it negative 7th? Yeah, it should be negative 7th. Did I tell you that here in the earlier part? That should be to the negative 7th, right? The vacuum permeability is negative 7th. That's my bad, okay? So it should be, where did I really messed up all the way up here, didn't I? Huh. Okay, it should be negative 7, okay? Okay. And then right here, so 2 times 10 to the negative 7th, okay, times 200 over r squared, okay? This is 0.01. Or not, oh gosh, I'm totally messing up. You can tell it's really late, right? It's almost like my bedtime, okay? 0.02, okay? Or 0.01. 0.01, that's what it is, okay. The C is about to stand for crash out, okay. There you go, okay? And then you end up getting that the magnetic field, right? If you punch that into your calculator, you get 0.004 Teslas, which is the same thing as 4 milliteslas into page, okay? And you probably don't even need to do really any math to get this, okay? Because you should know that the net field would be equal to 3 milliteslas into page, right? Because the into page field is stronger than the out of page field. Now, how can we make that B field? We want to increase the total magnetic field but not change the direction, okay? Well, notice how we had to subtract the two fields because they opposed each other. What if they both went in the same direction, right? We can do that. Let's do that, right? How do we make them go in the same direction? Right now it's going into the page. And so we don't want to touch the green wire because it's perfectly fine. How do we get the orange wire to also go into the page? Oh, wait a minute. Our right-hand rule tells us that right now it's going to come out of the page, right? Wait, but if I flip it, oh, now it's going to go into the page. That's what we need. So if what we can actually do, okay, is if we reverse the 100 amp current, okay, so it also makes an into the page, okay, B field at point P, okay, and then both currents now go into the page, okay. Okay, and then for this next example, is this the last example? No, there's a table in the back we need to fill in too. But for this example right here, okay, so we're going to draw the direction of the net electric or the net magnetic field at point P in each of the diagrams, okay? This is pretty straightforward, okay? All you got to do is right-hand rule on each of these wires, okay? And also there is an important thing to note. It does say let I equal 2I, okay? Which just simply means that if you have a lowercase I, it's going to be weaker than the uppercase I. So here we go. We have two uppercase I's, okay? and they're coming out of the page. So it's going to be, you can't see that, right? I have to zoom out. It's weird because these examples are so small, but my hand is so big, right? Okay, out of the page, it's going to go counterclockwise. Out of the page, going to go counterclockwise, okay? So here's what I'm going to do. I'm going to use blue and light blue, or sorry, green and light blue, okay? This is going to go around this way, okay? And then this is also going to go around the same direction, okay? Okay? And at point P, you're going to notice if we stretch this circle out, right? Point P is going to go about up this way, okay? And then you're going to notice that for the other one, if we stretch it out, it's going to go about down this way, okay? We've done that example, okay? And then you have a net field going to the right, okay? Okay, and the other one, right, we have I coming out of the page, okay? That's going to go also counterclockwise, okay? And then the other one's going into the page, which is going to be or clockwise, okay? Okay. And then B, right, so the B field at the point, if we stretch this out, it's going to go up and to the right, okay? And then this one, if we stretch it out, it's going to go down and to the right, okay? Ooh, okay. And you get a net B field going directly to the right, okay? Okay, here we have both are going into the page now, okay? Into the page is going clockwise, into the page going clockwise, okay? So we get both are going clockwise now. Okay. And if we do that, right, we stretch those circles out, you should get right here that the blue one is going to go up and to the right. Okay, I think my pen's running out of ink. That's why it's not really showing very well. And then here it's going to go up and to the left. Okay. And then finally, you'll see that the B net is going straight up. Okay. Pretty straightforward, right? I think you could have done that on your own, right? Now here we have both going into the page, but this one on the left you can barely see is actually lowercase I, so this is going to be weaker, okay? So what's going to happen is you're going to have just a little bit of magnetic field from the left wire and a lot more from the right, okay? So into the page it means clockwise, okay? Okay. And then into the page here also means clockwise, okay? Now, there's going to be a lot more influence from the blue wire than the green, okay? So the green wire is going to go down and to the right, okay? But there's going to be a lot more influence from the right wire, so this is going to go up this way a lot more, okay? So what's actually going to happen is their net magnetic field is actually going to be a little bit closer to going straight up, okay? And I think you can use the parallelogram rule for that too. Okay, that's what I have drawn. Is it kind of makes a parallelogram. However, if you just know that the blue should be stronger, then then you just need to show that it's closer towards the blue than it is towards the green. Okay, and then here again we have our weaker one is on the right now. Okay, so we're going to do again into the page is going to be clockwise. Okay. And then out of the page is going to be counterclockwise. And remember, this is the weaker one, so it's not going to have as much of an effect. So here with the green, right, this is going to go down and to the right, and it's going to be stronger, okay? And then the blue is going to be weaker. It's going to go down to the left, or down and to the left, yeah, okay? And so you should notice that ultimately what you end up getting is that the net field should go more towards the green, okay? Pretty straightforward, right? Nothing too crazy yet, okay? All right, there's that. Now let's fill in this table in the back here, okay? And we're going to do it really quickly because we want to compare and contrast gravitational, electric, and magnetic field. We've looked at these 3 different types of field over the course of our physics career, okay? So now we're taking another look at them, okay? Gravitational field, G newtons per kilogram, right? They act on objects with mass, and it's created by objects that have mass too, okay? You know that's how gravitational field works. We used F equals mg as an equation for the field, the force exerted by the field. This is the equation for strength of the field, a distance r away from some point source. Okay, you do this in circular motion, right? Okay, electric field. Okay, our symbol for that is E, okay? The units, do you remember the units for electric field? It's very similar to gravity. It's newtons per coulomb, okay? It acts on objects with charge, okay? Created by objects that also have charge, okay? We used this equation. This is the simple one, okay? E equals QE, okay? And then this is the electric field. More general equation is E equals KQ over R squared, okay? Notice the similarities there. It looks very similar, doesn't it? Okay. For a magnetic field, we've been using B, okay? And there should be arrows above these because they are vectors, okay? And the units is just Teslas. Wait, what happened to the newtons? Okay? Teslas is a different unit, okay? And it acts on objects. So magnetic field acts on objects that have moving charges in it, like wires with current, okay? Okay? And it's created by objects with moving charges. Okay, so again, those wires, right? The wires can actually act on each other. We'll look at that soon. The basic equation for this is, there's two of them. The magnetic field is equal to QVB, or, okay, it's equal to F sub B equals ILB, okay? And there is technically also attached to this a sine theta, okay? And we'll get more into that later, okay? And then the basic equation for the field we already did is B is equal to mu naught I over 2 pi r. And the main thing to point out here that I really want you to notice is that each of these equations, these final equations, all have some sort of constant in them, okay? Whether it's G or K or M naught, okay? There's some sort of constant in those equations that kind of, that's kind of a similarity that they all have, right? They're all defined by some constant that we use, okay? All right. Well, there you go. Have fun, make good choices, okay?